specifically the impact that renewables will have on the existing power grid and how it'll evolve over the next 10 to 15 years. And what you'll see, actually, Anna's talk was a great precursor to what I'll discuss, because many of the ideas that she presented will have natural hooks in some of the problems that I'll describe in terms of mechanism design, pricing, in terms of posted price mechanisms. But what I'll focus on is how techniques from optimization, namely optimization leveraging on samples or data derived from some unknown distribution, can be used to optimize the kinds of, optimizing the kinds of applications that arise in power systems with high penetration renewables. Okay, so when we say uncertainty, what do we mean by that? There's two forms of uncertainty that we'll consider in this lecture. One is in the form of supply. So, many states have very aggressive renewable portfolio standards to increase the amount of energy that's supplied from wind and solar. Hydro is also renewable, so dams or pumped water storage, but those are limited in terms of the geographic constraints. If you want to build a hydro facility, you need a mountain and a river, so there's not many places you can do that. So the supply of power from wind and solar resources, unlike hydro, is highly variable. And by that, I mean that it's not dispatchable directly. So the amount of energy you have available to you at any given moment of time is a function of the wind speed or the solar irradiance. It's intermittent, so it fluctuates wildly. You can go from, so a wind farm can go from operating at full capacity to 0 in half an hour or faster. Solar can fluctuate at much faster timescales. And the underlying physical processes by which these variations are determined are very difficult to model, which in turn makes it difficult to forecast what the power production will be from a wind farm over, say, 24 hours. And so I've tried to convey to you how this variability actually manifests itself in reality. So this is data taken from the Pacific Northwest. The first figure here represents or shows the total power production in the Pacific Northwest from wind over a day for every day in 1 month. Okay, so you can see that there's huge day-to-day variability in terms of the power production profiles from wind. This trace again represents power produced in the Pacific from wind in the Pacific Northwest over multiple weeks, and what you can see is that at some point wind just dropped and was totally absent for about 2 weeks. Okay, so if you're reliant on renewables to meet demand, okay, a large fraction of demand, how do you do this when you face such variability in the supply? Okay, you have to back it up, but this backup has to be done in an intelligent way, which leverages on techniques from stochastic optimization. Finally, this figure just represents the difficulty in forecasting. So this is a 24-hour head forecast of wind, the prediction error as a function of the prediction horizon for wind power production in some region. So you can see the confidence intervals can be quite large relative to the expected value. So again, a basic question is, how do you schedule dispatchable generation like coal and natural gas given uncertainty in renewable generation that has to be absorbed into the system? So that's a basic optimization question, which is highly non-trivial given the underlying constraints embedded in the power system that you have to satisfy. And by the way, if there are any questions, please feel free to stop me. So another source of uncertainty or emerging form of uncertainty will mean demand. Okay, so today demand is largely inelastic. Customers see a flat rate. Most customers see a flat rate for electricity, and they consume, not taking into consideration what that price actually is. And so we can predict demand to within extremely high accuracy, say 1 to 2% mean squared error, 24 to 38 hours in advance. And so that simplifies power system operations dramatically in the sense that you can schedule resources in the power system to meet expected demand, and any residual imbalance that manifests itself in real time will be quite small relative to the forecast. But there's a move to turn the demand side into a controllable resource to compensate fluctuations in renewable supply. So instead of tailoring supply to follow demand, you might tailor demand, flexible demand, to follow a variable renewable supply. So there are many ways in which you might control demand, either through price, time-varying price signals, or more sophisticated incentive mechanisms. But the point is, by injecting some form of excitation in the demand side, you might excite nonlinear dynamics or dynamics which were previously unseen, and therefore increase the uncertainty in the resulting demand profile over time, thereby making control of the system more challenging. So in order to actually control the demand side in a way that mitigates uncertainty, you need techniques from online learning and stochastic optimization, which can simultaneously optimize the system while learning the underlying model of demand so as to converge to an efficient operating point quickly. So there are basic problems in online learning which emerge here that I'll touch on, which involve nice trade-offs between exploration and exploitation. Okay, so the basic agenda, I'll quickly finish my discussion regarding power system operations today. Again, the models I'm going to present are almost, cartoonish, but they're just meant to give you a basic idea as to how operations what they actually look like today. Then I'll talk about a number of problems. One is related to optimizing power systems with uncertainty in the underlying problem's input data, namely in the form of renewable supply that's going to be available to you. Another problem I'll discuss is how you might dynamically price or incentivize demand response over time in the absence of an accurate model, or in the absence of a priori knowledge of how demand will respond to the price signal that you send to them. And then if I have time, I'll talk about an experiment we did with real electricity customers in New York City, which revealed some very interesting insight as to how consumers actually react to price. They're actually quite irrational. They exhibit behavioral biases, which are well known in the behavioral economics literature. But the point is, there are interesting opportunities, I think, to design mechanisms and incentives which leverage on these biases, or perhaps exploit them to operate the system efficiently. And then Adam will talk about, this is a very brief summary of what he'll discuss, the role of algorithmic mechanism design and related problems in electricity markets. Okay, so again, I said the system is very complex. I'm going to present a very simple description. So this is the control room in the Northeast. So this is the grid is divided into multiple regions with system operators being responsible for balancing the power system in their local region. So PGM is one such system operator, and they're responsible for balancing this blue area here, which spans Pennsylvania, New Jersey, Maryland. They coordinate transactions, market transactions between hundreds, even thousands of agents on daily to minute timescales. They solve NP-hard optimization problems every hour. I'll describe that in more detail briefly. So the system is quite sophisticated, but the basic objective is to schedule supply to balance demand on a second-by-second basis. This should be done in a least cost fashion while ensuring some level of reliability in operating system or robustness to failures or contingencies. The market design objectives are twofold. First is short-run efficiency. You should design the market in such a way that the market participants are incentivized to reveal private information that leads to efficient operation of the system in the short run. Okay? And this is cost information primarily. There's also a long-run efficiency objective, which is related to the creation of market signals in the short run, which incentivize expansion of transmission and generation facilities, okay, in the long run, which are comprised of the right mix. So you want to create market signals which incentivize the building of a transmission line in the right place, namely the place which will maximize social welfare. Similarly with generation. So these are markets we won't touch on, but this just gives you a sense as to the huge variety of an interplay between markets and operations and power. Okay, so operations. How do power so what do we mean by power system operations? The stylized model is two-stage. So day in advance, the system operator has a forecast of demand, this dashed line. It dispatches generation, okay, and again in a least cost fashion to meet the expected demand, this forecast. Okay, this is done myopically in the sense that it doesn't take into account the fact that it'll have a recourse opportunity, right, to adjust or compensate imbalances based on more accurate information in real time. Okay. So the real-time adjustment obviously will compensate any imbalances which are realized based on the day-ahead schedule, which was determined myopically. Okay, so this is a two-stage stochastic program or optimization problem which is solved in a decoupled fashion. If you notice here, again, demand can be forecast. So this is actually real data. Demand can be forecasted to within very high accuracy. So the resulting imbalance in today's system in real time is in general quite small. So the cost of the inefficient use of information in this setting is small. And there are simple stylized news vendor problems which reveal this trade-off in a much cleaner way. So at each stage, the system operator solves, like I said, an optimization problem known as optimal power flow. So day ahead, it'll schedule generation to minimize the cost of supply to satisfy a bunch of constraints. So supply equals demand according to Kirchhoff's laws. The flow of power across the network should satisfy transmission capacity constraints. Generation set points should meet generator constraints. And you might have voltage magnitude constraints. So the voltages at different nodes or buses in the transmission network should satisfy certain bounds. Okay. So this is in general a non-convex problem, both because of Kirchhoff's laws. These are essentially indefinite quadratic equations in the complex domain, and the cost of supply. Generators have startup costs. Okay, so starting up a generator will incur some fixed unit of cost, regardless of what its operating point is, and so that manifests itself as binary decision variables in the problem. In the absence of these startup costs, the OPF problem is essentially a quadratically constrained quadratic program, which is non-convex. The quadratic constraints are indefinite. So those of you familiar with these types of problems know that the most common relaxation is the semi-definite relaxation. And there are some recent results which have shown that for certain network topologies, these relaxations are actually exact. And Stephen Lowe has a very nice survey paper formulating this problem and presenting in detail the exactness conditions for these convex semi-definite relaxations. Okay, so markets. Again, the system operator is minimizing the cost of supply, but this is private information which agents have to reveal. Okay, and this is procured through a market. And so there are interesting questions related to efficiency of these markets at Nash equilibria if they exist, which they may not in some cases. So many, and I guess the important thing to point out is agents are bidding supply functions which reveal their willingness to produce power as a function of price, and demand reveals its demand curve, which reveals its willingness to pay as a function of its consumption level. So these are, in general, infinite dimensional bids. Okay. So many people have studied the efficiency of these types of markets. I won't delve into the details here. Adam will touch on this later. But the point is, there's very little which is known about the existence or lack thereof of Nash equilibria and supply functions over networks, power networks, even linear approximations of the power network. Okay, so very interesting problem. Okay, so I'll skip over this quickly because I touched on many of these issues earlier. The increase in renewable supply in the power system is going to amplify, okay, the amount of uncertainty. So whereas the realized demand profile previously was very close to the forecast, in this setting, when you have a lot of wind on the system and it's treated as negative load, namely the system operator has to take it, you'll realize a trajectory which is more variable, has ramps, and can be quite different than the day-ahead forecast. And the pink intervals there represent 90%, or I think in this case 70% confidence intervals. So even forecasting day in advance is quite challenging, and the myopic approach that I described to you earlier will turn out to be quite inefficient in this setting. Yes?
So if you realize that you're falling short of the demand, how long does it take before you can, is there a lead time in generating more power to sort of fulfill the demand?
Yeah, so you can think of this as, so there are different ways of compensating imbalances at different timescales. So in terms of markets, or the use of market mechanisms to compensate imbalances, the fastest timescale market, depending on the region, is roughly 5 to 15 minutes in advance of delivery. So you can clear a market 5 minutes before you actually have to deliver power. Then in real time, there are automatic control mechanisms which will compensate any residual imbalance on the second or sub-second timescale. Okay, so the lead time is about 5 minutes for the real-time market, 5 to 15 minutes. So the point is we need new optimization algorithms. And Adam will touch on results in the single node case in the absence of a network related to which have a firm grounding in inventory control theory or multi-period news vendor problems. Okay. Again, so this gives rise to the need to perhaps leverage on demand-side flexibility to compensate this variability in supply with large amounts of renewable in the system. So I'll touch on both of these problems moving forward. Okay, so now optimizing power systems with renewables. The stylized problem we'll discuss is as follows. I'm not going to kind of open the hood here and unpack all these equations, but this is the basic problem that we'd like to solve. You'd like to minimize the cost you would incur, okay, with probability no greater than alpha, okay, subject to your constraints being satisfied with probability at least 1 minus epsilon. Okay, so this is essentially in epigraph form a chance-constrained optimization problem, which again is NP hard in general, even under some simplifying assumptions that I'll make. I'm going to assume that the power flow equations are described by linear equations. This is known as the DC power flow approximation. And any recourse decision will have a finite dimensional parameterization in the uncertain variables to which it's a function of. So this eliminates the complexity associated with the infinite dimensionality of the recourse decision space. Okay, so we'll end up with a finite dimensional chance-constrained optimization problem. And now we'll talk about how techniques from stochastic optimization might be used to address or solve these types of problems. Yes?
Sorry, I missed it. So what do I play with?
So I'll come back to that.
The prices or
No, so here, yeah, that's a good question. Your objective, like I mentioned earlier, was to determine generation set points over multiple periods to ensure that the system is balanced with high probability.
So I have my own generators and I can turn them on because...
No, there's a system operator who controls many generators. So think of a social planner who has access to hundreds of generators connected to different parts of the network. And that system operator, and there's also wind, which is injecting random power, okay, or variable power over multiple time periods. The system operator would like to determine how to schedule these generating resources in such a way that this cost is minimized. This is a form of value at risk, while ensuring that constraints are met with high probability. This is in contrast to a robust formulation in which you might require that constraints are met with probability 1.
But there's no strategic behavior going on.
No strategic behavior. This is purely an optimization problem. So I'm assuming the cost. So I mean, this is a problem that actually would be solved, right? These are costs which are revealed to you, but then you have to optimize given those revealed costs. Is that clear? Any other questions? Okay. So I have to speed up a little bit. So more abstractly, this is the problem we're interested in. You'd like to, so x is your decision variable, it's n-dimensional, and again, you can interpret x as being generator power outputs. Again, over multiple time periods. Delta is your uncertain variable, so it could be wind or solar power or even network topology. It could be used to represent variability in the network topology. You may or may not have a line available to you in real time. Epsilon is this acceptable probability of constraint violation, so you'd like your constraints to hold with probability at least 1 minus epsilon. And so, again, because I've put the problem in epigraph form, it's without loss of generality to assume a linear objective in this setting. So these problems are essentially equivalent under the assumptions that I made below. So the solution of this problem requires both an assumption and knowledge of an underlying distribution. Some additional assumptions we'll make is this set X, it's deterministic, it's known, closed, and convex, and the function f is assumed to be convex in your decision variable x for each delta, for each realization of the uncertain variable delta. It is not necessarily jointly convex in x and delta or convex in delta. Okay, we only require convexity in x. And so if you knew delta, this would be a convex optimization. But we don't. And so this problem in general is non-convex and NP-hard, actually, even for very simple forms of f. If x is biaffine in x and delta is non-Gaussian, then this problem turns out to be NP-hard, even if delta is uniform. There are ways of approximating these problems from within using so-called CVAR constraints, which arise from Bernstein inequality approximations of these probabilities, but I won't get into that. But there's a very nice paper by Nemirovsky and Shapiro. So I think the biggest problem is this assumption, at least in the context of power systems, that you know the underlying distribution P. Right? In practice, you don't. And even if you did, the problem would be difficult to solve. And so the question that we'd like to answer, and I think this is a broader question to the community, is how might one leverage on data taken from wind farms or solar farms to approximate solutions to this hard problem in a computationally efficient manner. And so let's imagine we're able to extract IAD samples from this distribution P, which may or may not be known. How might you use these samples to efficiently calculate feasible solutions for this problem? I won't touch on the issue of optimality, but we'll focus on feasibility here. So the most natural approach would be to approximate this constraint using the sample average approximation of the underlying distribution. This clearly gives rise to a mixed integer program. Think of, yes, so it's not difficult to see that because of the indicator function here, enforcing this constraint is essentially equivalent to a combinatorial optimization, which is, again, difficult to solve in of itself. The advantage of using these representations is that as n gets large, the empirical distribution will converge to the true distribution, and you'll get closer and closer to the true optimal solution for the underlying problem. But what we'd like to do is identify a way to solve this problem efficiently using convex approximations. So one way of doing that is to set the risk constraint, or the acceptable probability of constraint violation, equal to 0. This constraint then turns out to be equivalent to a set of random convex constraints, or more simply, a random sampling of your underlying constraint functions. So this is a tractable convex program. It is random because your feasible set is random. It's determined by the samples that you've procured. And as the number of samples gets very large, it's, I think, straightforward to see that the solution you calculate will converge to the robust optimal solution, not the chance-constrained optimal solution. So it will be overly conservative if the number of samples is quite large. So it's a very natural sample complexity question. How many samples do I need in order to ensure that the solution I calculate is feasible with respect to my original chance-constrained feasible set with high probability? Here, xn hat will denote, we'll use to denote its optimal solution. So here, calligraphic x sub epsilon is our, yes?
Robust. So what's the uncertainty over which it's robust?
Oh, so yes. So by robust, I mean if the random variable had bounded support. By robust solution, I mean that solution which is feasible for all realizations of delta over some support of the random variable. Okay. Those problems may or may not be tractable depending on how you characterize the support of the random variable.
So those are the deltas.
The deltas, yeah, the support of delta, the random variable, right? So this ellipse here, for instance. Okay, so there's a very elegant result by Campi and Calafiore from a number of years ago now, which says that if you procure a number of samples which is greater than or equal to this number here, then you're guaranteed that the random optimal solution you calculate will be in your feasible set with probability at least 1 minus beta. So here the sample complexity depends on beta through log, beta inverse, and epsilon through its inverse. Now the interesting thing is this result is distribution free in the sense that it holds for any distribution P under some regularity conditions which are quite, I think, weak. It depends linearly on the underlying dimension of your decision space here, n, as opposed to the VC dimension of the family to which f belongs to. It's independent of D, the dimension of your uncertain variable. It only relies on the assumption of convexity of the constraint function f and x. So what we've done is we've taken a problem which is quite difficult to solve in general, constructed a random convex approximation which is guaranteed to yield solutions which are feasible with high probability. They might be conservative, but if the number of samples is not so large, then you would expect they'd be close to optimal. But that's actually an open question as to how one might bound the optimality gap incurred by these random optimal solutions.
Question. So for each scenario, you'll be having a decision variable. How do you aggregate all these decision variable x in reality?
It's not for each scenario. You calculate one decision variable x.
But like renewables can be lower than the sometime, and demands can be higher, and you must meet the demands with the generations. So there has to be just one variable.
Yeah, so what I did was earlier I made this assumption here that my recourse decisions have a finite dimensional representation. So for instance, think of recourse as being affinely parameterized in certain variables like wind. So when wind realizes itself, I'm requiring that the decision I take is affine function of that recourse. And so I just end up with x here is just all of these decision variables unraveled into a single vector. Is that clear? Okay. Okay, good. So this is nice, but there's a caveat. There's this assumption that the samples you take are actually taken from the true distribution. In the context of power systems, there are two reasons why that might be unreasonable. One, the amount of data you actually have available to you is not so much, right? So if we're using samples from wind farms, many wind farms have only been around for, maybe 5 or 10, let's say 10 years, right? If your samples are daily wind power profiles, well, then you only have roughly, 3,600 samples, right? These predictions require that you have samples which are on the order of 1 over epsilon. If epsilon is quite small, then you may require millions of samples, which you may not have available to you. So you might have to rely on a model or an approximation based perhaps on an empirical distribution formed by the limited number of samples that you do have available to you. Okay? So the basic question then is, can one use similar techniques to efficiently calculate solutions which are feasible for this original chance constraint problem using samples which come from the wrong distribution, okay, or a model. So you might think of here p hat as being a computer model you have for wind farms from which you can efficiently generate IID samples. And again, these are available to practitioners, and this can be done. The naive thing would be to just take these misspecified samples and use the random convex set generated by those. Okay. If the distributions are close, you would expect that these samples would be close, or the histogram associated with these samples would be close to the histogram generated by samples taken from the true distribution to which you don't have access. And so one would expect that given some notion of closeness between distributions, you might be able to generalize these previous results to the setting in which I've described here. So we need some notion of closeness or ambiguity in distributions. And so what we'll do is we'll assume that the model and so our model, our incorrect distribution, and the true distribution live in some ball of radius r centered at your model distribution. Okay, so again, if P was formed as the empirical distribution given some finite number of samples from the true distribution, you could construct these balls using Wasserstein metrics or Kolmogorov metrics such that P would live in this set with high probability, depending on the underlying number of samples you do have available to you. But for now, we'll assume that the true distribution lives in this set with probability 1. So here, rho, we measure the radii of these sets using some distance metric or distance over probability measures. So examples are total variation, Hellinger, relative entropy, chi-squared. And the important thing here is, as the radius goes to 0, we recover the previous formulation. And so one property we might like to, or or a feature that we might like our results to satisfy is that these sample complexity results should recover Campe and Calafori's results as the radius of this ambiguity set goes to 0. We have a result of that type. So this is the sample complexity result that we end up with using samples from the misspecified distribution depends not on 1 over epsilon, but 1 over nu, where nu is a function of both epsilon and the radius of your ambiguity set. So if the number of samples satisfies this inequality, then these random optimal solutions you calculate using misspecified samples will be feasible for your original problem with high probability. And nu here is a decreasing function of R clearly. So as R goes to 0, nu for these various metrics goes to epsilon. For the chi-squared metric, as R goes to infinity, namely as the radius of your ambiguity set gets very large, the effective risk or probability of constraint violation goes to 0 and the number of samples you derive blows up. An important thing to point out is that under total variation, for instance, the radius of the ambiguity set cannot exceed epsilon. So epsilon here, or the acceptable risk of constraint violation that you can enforce cannot be smaller than the radius of your ambiguity set, as opposed to the chi-squared metric. And that has to do with the fact that chi-squared is a far more restrictive measure of distance than total variation or Hellinger. So this is, I think, a very nice generalization of these previous results. And in the sense that it answers, I think, this important question in power systems related to the use of data that might be coming from inaccurate distributions and how you calculate dispatch decisions. Yes?
I can imagine situations where a forecaster which uses last 10 days wind may be more accurate than even samples. Do you have something similar to that?
So using samples from that might come from a distribution which is closer to the distribution to.
So like I may learn a forecaster which looks at last 10 days wind production and then forecasts like day 11's wind production, and that may be more accurate than even looking at like samples of wind production for that same day over multiple years. And if that has a smaller forecasting error, would something similar hold in that?
Yeah, I mean, clearly a trade-off would emerge, right? I mean, there's a trade-off between the number of samples you require and the accuracy of the forecast, right? So here, really, R is a coarse measure of accuracy, right? So that's great. And here, I mean, this is just the perturbed risk level here as a function of R, and you see that it tails off as differently for different metrics as R goes to infinity. Okay, good. So there's some open questions here. I mentioned earlier, can one construct probabilistic bounds on the optimality gap associated with solutions generated by these approximations? It would be interesting. There is some initial work that's focused on generalizing these types of results to non-convex constraint functions F. So this would be useful for the case of the AC power flow problem or this quadratically constrained quadratic program representation. And finally, there are interesting questions related to parallelization. I mean, the number of samples you end up having to generate, and in turn, the number of constraints you have to enforce in solving these problems can be quite large. So is there a way of decomposing the solution of this problem into much smaller problems where, let's say you have 1,000 constraints. Instead of solving one problem using all 1,000 constraints, you solve 10 problems, each of which has 10 constraints. You take only those constraints which are active in each of the subproblems and solve another problem which only uses the active constraints from the smaller problems. So this is a form of importance sampling near the optimal solution. Can one prove anything about hierarchical methods to approximate solutions to these types of problems? This is a hard question, but it's an interesting one. Okay, so now let's switch gears. I'll talk about an online learning problem related to dynamic pricing of flexible demand. And the basic idea here is you have demand, customers who are willing to reduce their consumption. Their willingness to reduce as a function of price is private information. Okay, you don't know this. So as a utility or an aggregator, you'd like to set a price which maximizes the cost savings you derive, which are really the benefit you derive minus, as a function of the demand reduction, minus what you have to pay to them. Okay. If you knew the demand function, then this would be a straightforward optimization. But in practice, you don't. And so we consider a posted price approach where the utility will, well, I'll get to it. Okay, so here's a picture which makes this clear. So you have an aggregator utility which interfaces between demand-side resources, say households, and the wholesale market. The aggregator would like to buy demand reductions from the residents. Using that demand reduction, it'd like to sell an energy product into the wholesale market. So a reduction of, say, 10 kilowatt hours from the demand side can be viewed as a supply of 10 kilowatt hours in the wholesale market. That reduction is going to be random, okay? So the amounts that you offer into the market, the wholesale market, is also random. And if you turn out to be short of what you had originally offered, you have to pay a penalty. And so there's an interesting two-sided optimization problem which arises here. What price do you set for customers on the one hand, and how much do you offer in the wholesale market on the other hand? Okay. And more basically, yeah, so that's the basic idea. So let's talk about the wholesale market. If you recall, I had mentioned earlier power systems are generically operated. Dispatch decisions are taken in two stages, day ahead and real time. Well, these dispatch operations are coordinated with markets, which clear day ahead and real time. So nominally, you'll have a day ahead price, which I'll call pi, and real time and balance prices. And I'll get to those in a second. So if you offer a quantity X day in advance, you'll receive a day ahead payment, which is pi times X. You realize a supply, S. If you're short, you have to pay according to the shortfall imbalance price delta S. If you're long, you get paid according to the long imbalance price delta L. And we'll make some simplifying assumptions on the relationship between these prices, which we'll also assume to be fixed and known. Okay. That can be relaxed, but for the purposes of simplicity in this talk, we'll keep those. And there are also other details we're ignoring in terms of more complex bids that this aggregator utility can make in the wholesale market. So this is actually, these markets are run today. Aggregators can take small residential resources, be they thermostatically controlled loads, so air conditioning units, small energy storage devices, either in the form of electric vehicles or wall-mounted batteries, and they can sell this capacity into wholesale markets. This is known as the proxy demand resource product. And there are several pilots which have been run in California in the last couple of years. So this is real. So how does the aggregator elicit the response from the demand side resources? So like I said, we take a posted price approach. So the market repeats over multiple days. On each day, T, it broadcasts a price PT. Each household or customer will respond with some reduction, SI of T. Okay. For that reduction, the customer receives some payment, PT, which is a uniform price across customers, times SI of T. There's one caveat that I'd like to mention. If S is taken to be a demand reduction, well, clearly that reduction has to be measured relative to some baseline, which you may or may not know. I'm assuming you know the baseline, okay, in this setting. There's an interesting question as to how you might actually elicit or estimate baseline information from customers. And there's some nice work that's been done here at Berkeley and Kambashwar Pula's group related to these questions. So, but I'm going to sweep that under the rug for now. I'll come back to that later. So S of T we'll call the aggregate demand reduction at time T. Fine. So we need some model, okay, to begin to even reason about as to how we might set prices. So for the purposes of this talk, we'll assume that the aggregate demand function, okay, is an affine function of price subject to additive and unobservable shocks, okay, which are independent, identically distributed over time. Okay. So we'll assume that you have an affine parameterization, but we don't assume that the utility or aggregator knows these parameters, nor does it know the distribution of the shock, which, because of the structure of this problem, the distribution will actually turn out to be important. So the aggregator has to learn these things over time. So now let's take a look at the aggregator's profit in total. So again, what are the aggregator's decisions at each time T? On the one hand, it has to offer a price to customers. On the other hand, it needs to make a bid into the wholesale market, X of T. Right? And so it derives a profit in the wholesale market, which is this term on the left, and a cost, which is what it has to pay for getting some demand reduction, S of T. S of T is random. So what the aggregator would like to do is to calculate the price and contract energy bid, which would maximize its profit. If it knew the underlying distribution and demand parameters, then this is essentially a straightforward news vendor problem, and you can characterize the optimal price and energy bid, which would be time invariant, clearly, because I've assumed that everything is constant. I won't get into the structure here. Adam will spend some time talking about news vendor problems. But the point is, if you had full or perfect information, the problem is trivial. But what if you don't know these parameters? We take an online learning approach. Okay, so on each day t, the aggregator, we assume, has access to past market history, which is the sequence of previous posted prices and previous demand reductions. Okay, we're assuming it can measure demand reduction directly. And so it offers a quantity xt into the wholesale market, posts a price pt, and observes a demand reduction st. Okay, so that manifests itself as some data point here. And this repeats. Okay, and over time, as it sets different prices, it'll see different demand reductions, and it can potentially construct estimates of the underlying demand model through which it might myopically optimize price and quantity. But there's an important property that the price process should satisfy in order to prevent so-called incomplete learning, and that's related to the rate at which prices converge. If prices converge too quickly, then you may converge to perhaps an estimate of the model, which is inaccurate, which would in turn lead to your setting prices at inefficient levels. And so there's a need to ensure some dispersion or excitation in the underlying price signal you send to the market so that you can efficiently learn the model asymptotically, or learn the model exactly asymptotically. But clearly there's a trade-off, right? The dispersion should not be so large as to lead to poor performance in the long run, namely unbounded regret. So how do you set this dispersion parameter, which I'll specify now in such a way that you have good performance? So again, the pricing policy here should be causal, namely, it should only be a function of your past information. We'd like the price sequences you generate to be consistent with respect to the Oracle optimal price, similarly for the energy bid. And a basic metric, whether this is the most natural one to use, is regret. And so we'd like our regret to vanish, the average regret to vanish asymptotically. Or namely, we'd like our t-period regret to be sublinear in t. So here we're measuring regret as the expected profit you would derive from under the Oracle optimal decisions over t periods minus what you derive using your policy. Okay, so standard definition. And so the basic technique we'll use for demand estimation is straightforward. It's a least squares estimation. So you have price demand reduction pairs over t periods. You fit a linear model to that data. Invariably, it'll be inaccurate. We also need to construct an estimate of the underlying demand distribution. So what we do is we take the residuals associated with this linear fit. We calculate the empirical distribution associated with those residuals, and we use that as our approximate quantile to construct our approximate quantile function, which, if you recall, our energy bid depended on. Okay, this is the basic approach to model estimation that we're going to use. So one natural thing to do would be to interweave a myopic approach to pricing with this model estimation scheme, which would be at every day t, take your estimates of the underlying parameters and set the price in order to maximize your one-step profit, assuming those estimates are exact. What you can show, so here we'll just do a simple simulation, is that you may end up converging to the wrong estimates. Namely, you may end up with incomplete learning. And so here, your estimates of the model parameters for the demand function converge to incorrect values. So the dashed lines are their true values. The red lines are sample paths of your estimates over some finite horizon. So they converge fairly rapidly, but they come to the incorrect value. You end up with similar behavior for your quantile, price, so on and so forth. Okay. So in order to prevent a complete learning, I hinted at a strategy earlier. You might take your myopic price and introduce some dithering or perturbation to the price to ensure that you have enough dispersion or variation in your inputs so as to guarantee asymptotic efficiency in your demand model estimates. And so what we do is we use a very simple policy. There are many other policies that one might propose which would yield similar results, but for simplicity of this talk, this is the one I'll discuss. At every odd time step, you use the myopic price. At an even time step, you take your myopic price from the previous time step and you add a perturbation which is order 1 over root 4t. Okay? And what you can actually show is this is the optimal size of perturbation that you should add in order to guarantee that you achieve the optimal order of regret in terms of its dependency on t. This signal introduces enough dispersion so that you can ensure asymptotic consistency in your demand model estimation, but the dispersion is not so much that it leads to unbounded or linear regret. Okay? And the C here is some parameter that you could optimize, and I won't get into that. And so what you can prove is, under this policy, this perturbed myopic policy, which introduces this excitation to the myopic price, you can achieve an order of regret which is square root t, and this is actually optimal. You can prove this. There are several nice papers by Asafzivi, Keskin, and Bezbis which look at similar problems in which they establish lower bounds that hold for this setting as well. What's interesting here is I've assumed that the wholesale prices, the prices in the wholesale market are fixed. If you allow those to vary, this introduces some form of costless exploration in the myopic decisions. And so if those wholesale prices vary, the variation from period to period is strictly positive, okay, so here epsilon is some positive constant, that you can actually guarantee, you can prove that the myopic policy achieves an order of regret which is log t. I think the interesting thing to point out, however, is that the constant which shows up ends up being inversely proportional to 1 over epsilon squared, okay? And so the amount, although asymptotically you achieve a log t regret, the constant could be extremely large if the exploration in the underlying wholesale price, or this costless exploration, is small. Okay, so going back to our perturbed myopic policy, you can show that this perturbation is enough to ensure consistency. Okay. This is interesting here. So this is actually the price sequence we generate. So there's a huge amount of variation. Okay, this may not be palatable to customers. There are other ways of implementing these perturbations. You could employ phased exploration and exploitation schemes where you keep the price fixed for a number of periods and then allow shifts over over some intervals of time which increase logarithmically with time. But and I'll get to a point that is related to this at the end. Okay, so there's some interesting open questions. One is, here the metric we've used gives you a good notion of asymptotic performance. But in practice, these programs will run over finite time. So it'd be interesting to look at policies which have provable finite time behavior. Second, we've also assumed that demand is, in some sense, stationary. In practice, the customer population may evolve over time. Customers may be coming in and out of the program. How do you capture that non-stationarity in the policy you use? You might also experience customer fatigue effects. If customers, see a sequence of very low prices, they may drop out of the program after some period of time. So building these non-stationarities into the model would be interesting. I think the point I alluded to earlier is related to kind of this idea of needing a baseline. So in order to measure demand reductions, you need a baseline by which to measure that, right? And so that's something you don't know. And so there are various ways of doing this. One way would be to just estimate it using similar days in the past. Another way would be to use a mechanism in which the customer might be allowed to reveal a baseline. So how would you design such a mechanism so that it's incentive compatible to reveal your true consumption, what your consumption would have been in the absence of an incentive to reduce? So again, there's some nice work here at Berkeley that has addressed some of these issues. And finally, different incentive designs. Okay, so this is a very simple mechanism that we've proposed, but Are there other mechanisms, say lotteries, which might yield superior performance in terms of the amount of reduction you're able to produce per unit cost to the utility? And so I have a few minutes. I'll talk about an experiment we did which looks at these different incentive designs. We learned some interesting things. Okay, this was very qualitative, but I think it reveals some insight which could be useful in terms of formulating problems in this area. Are there any questions so far? I don't have it in this version. Okay, let me. Okay. There it is. There it is. Okay. Okay, so this was in collaboration with Consolidated Edison in New York City. So here our objective was to control air conditioning units. There are roughly 6 million wall-mounted units in New York City, each of which has a capacity ranging from 500 to 200 watts. So in total, the peak capacity, if they were all on at the same time, would be 12 gigawatts. That's equivalent to several nuclear power plants. So the basic question they've been doing this for quite a while using the more traditional incentive mechanisms that I just described to you. But the basic idea is, can you design incentives which would induce customers to reduce their temperature set point on very hot days? Because on those days, the utility faces a very high price for electricity in the wholesale market. Nominally, the price of electricity in the wholesale market is anywhere from $30 to $50 per megawatt hour. On these peak days, it can range anywhere from $1,000 per megawatt hour to $5,000 per megawatt hour. So it's very, very costly. The utility would like to shave the peak on these hot days. So the basic control architecture is that the utility has direct control of the AC units. So essentially switches that can turn these things on and off, and that control is done through the internet. And so by being able to control the switching of an AC unit, you can essentially affect its duty cycle, thereby changing the temperature set point at which it operates. So you can actually do temperature control with simple switches.
Just make sure the utility is controlling the AC in our...
Yeah, the customer agrees to participate a priori. And the way the events work is, a day in advance, the utility has some forecast of peak. It alerts the customer there's going to be an event tomorrow. Okay? And the customer knows what time the event starts, at 7 p.m. Anytime before that, they can opt out. Okay? At 7 p.m., the customer will increase their temperature set point by 5 degrees. Okay? And the event runs for 4 hours. And any time in the program, the customer can opt out. They can just say, look, I don't want to deal with this, and they drop out of the program. So really here, you can measure customer performance or demand reduction as a function of, in terms of the amount of time they stay opted in. Okay? So 4 hours would be the maximum amount, 0 would be the minimum amount. So if we were to use the posted price approach that I described earlier, you're essentially paying the customer the marginal benefit you derive from that individual by having his or her demand reduction, which in practice is quite small. It could be 10 cents per kilowatt hour or less. And so what you find is, in kind of this, and experienced this problem for several years, people are happy to sign up, but as soon as they start seeing payments, like, it's not worth my time. You're only paying me 20 cents to increase my temperature by 5 degrees for 4 hours. It's not worth it. Okay. So the key point here is individual action has low value leads to low value to the customer. Okay. But collectively, the action of many individuals, thousands or hundreds of thousands, is quite valuable to the utility in aggregate, right? And so the utility can actually save quite a bit of money by having 100,000 people reduce their temperature. So is there any way of, instead of paying each individual for their contributed marginal benefit, can you somehow pool the total benefit and design a mechanism which gives some people more and maybe some people nothing?
Lottery.
Exactly, right? And so the basic question here, how many of you would prefer 10 cents for sure, or $100 with a 1 in 1,000 chance? So how many people would prefer choice 1? How many people would prefer choice 2? So, assuming you're risk neutral, choice 2 is the irrational decision, but most people would go with choice 2, okay? So there are many behavioral biases which might explain this behavior, but I found this old paper by Laplace where I think he has a beautiful explanation. He says it's principally at games of chance that a multitude of illusions support hope and sustain it against unfavorable chances. So I'm not going to get into behavioral economics. We'll just assume that people might prefer these types of things. So this was actually inspired by some work done at Stanford by Balaji Prabhakar in decongesting transportation systems. So I saw this as a graduate student, and I thought, wow, this might, and that was many, many years ago, this might actually be useful in power systems. And so the lottery mechanism is structured as follows. So it's tiered. Okay? If you participate for 0 hours, you qualify for nothing. If you participate for in between 1 and 2 hours, you qualify to play for a tier 1 reward, which is $5. Okay? There's 50 of these. Okay? So I'll explain how the rewards are drawn. If you participate for 2 to 3 hours, you qualify for a tier 2 reward, which is $25. And if you stay for the entire amount of time, just 4 hours, you qualify to win $100. Okay? So, which is non-trivial. And there are only 2 of those rewards. So the program we ran actually only involved 200 customers. And so you could map these tickets to probabilities, assuming the customers know how many people are in the program, which they did. One thing, this is also a caveat, when dealing with kind of residential customers, you also have to take into account the fact that they have limited ability to actually, or time rather, to understand sophisticated mechanisms. So that goes back to a point that Anna was making earlier. Simple mechanisms are valuable in that they can be understood more easily by customers. So again, the drawing is as follows. If you qualify for tier 4, if you win, you take the $100 and leave the lottery. If you lose, you waterfall down to the next tier and are included in that drawing. If you win, you go out. Otherwise, you continue cascading down until you either win or get nothing and leave the mechanism. And so we had two groups, each of which consisted of 200 households. The lottery group and the fixed rebate group, which received roughly $2 per hour of participation. Okay, so that's non-trivial. That's much higher than what they're actually, the value they're yielding to the system. Okay, so we thought let's look at the extremes of this program and see if we can still show that a mechanism like this improves upon its non-trivial fixed payment. So there were 5 events over the summer, and these are the results. So what I've listed here are the statistics associated with the participation time in each group for each event. So there were 5 events. So consistently, the lottery group has an average participation time which is higher than the fixed payment group. And you also notice that the variance in the response was less. The interesting point is, I think one interesting point is that this difference was most pronounced on the hot day, okay, which was later in the program. And so somehow the lottery was more effective at sustaining customer participation on hot days than this fixed rebate incentive. Okay. So the average cost of the utility at the end of the day, in terms of the average marginal cost, was roughly 70 cents per hour of customer participation time in the lottery group, and again, $2 per hour participation time in the fixed rebate group. Yes?
What's the discrepancy in the sizes?
Yeah, so again, this is the real world, right? I mean, so we're controlling these units through the internet. There were times at which somehow units were not available. Either the customer had unplugged or there was some failure in their wireless connection at home, their internet connection. It's not
them opting out of
No. So these are not due to opt-out numbers. These are due to these are the number of customers who we could verify were available. Okay.
The split is always the same of the 2 groups.
What do you mean this?
Split into like the random and the lottery and the fixed.
What do you mean by the split? So there was 200, we allowed 200 participants in each group. And one thing I should mention is that customers self-selected. So when we opened the program out, we allowed customers to choose that here are these 2 incentives, you pick.
Okay, and every day the same group was...
Same group, yeah, yes. This was not meant to be a rigorous experimental trial. It was just meant to gain insight. Okay. So I shouldn't even call this experimental results. And so these are just histograms of the participation time in each group. Yes?
I mean, these things have been implemented now in many contexts. I think do these kind of incentives sustain in the long term? That if I if you run it for a year, I mean, do people sooner or later figure out that the average payment is low, so I should just...
No, that's a very good question, actually. I mean, the reinforcement effects, which I'll kind of touch on briefly at the end, are not, they haven't been well studied in programs which run for longer periods of time. But there is one insight that qualitative insight that we derived is there are ways of reinforcing kind of a customer's affinity to participate in these programs. And that's namely just giving them something small more frequently. And so if I boost the probability of very small rewards, that can amplify these biases to participate in these types of programs. So that's an interesting question. I don't know, but it's perhaps worth exploring in more controlled experimental environments. So again, these are just histograms. The blue is the lottery group. The red is the fixed payment group. And it's a histogram over participation times. And you can clearly see that the lottery group has a fatter tail on the right. Namely, people were staying in for longer periods of time. So this was the hottest day. Again, the difference is most pronounced on the hottest day. So on the hottest day, you can see that many people in the fixed payment group opted out immediately, while the majority of people stayed in for the entire amount of time in the lottery group. Okay, this is an interesting figure. So this compares the dependency of customer participation times as a function of the average outside temperature over the event time. So you notice so here the solid lines are the means, the dashed lines are the medians, and these boxes are the interdecile ranges. The participation time in the fixed payment group decreases with increase in temperature. But you also get an increase in the variance in response. And this goes back to this earlier comment I made at the very beginning of the talk, that incentives which aren't carefully designed might actually amplify uncertainty in the power system. Okay. Whereas in the lottery group here, you can see that the variance in response is somewhat insensitive to temperature variation. So is the average participation time. So interesting observation. Not enough data to say as to whether this holds in general, but I won't parse this table because I've gone over time, but the point I'd like to make is there are reinforcement effects, and the sequence of rewards matters. So we noticed that customers who received something initially and then lost, right, on average provided more to the system than customers who lost initially and then received something later. So there's some initial conditioning effect. So it's important to give somebody something initially so that you kind of somehow that leads to the largest amplification of this bias. So I'll stop there. I guess the one point I want to make is customers, they may not be rational in the normative sense, and so, using techniques from, online learning or stochastic optimization, which relies on data to build models, I think could be quite valuable in this setting, as it might allow for a richer class of models which could be optimized against. So that's it.
Quick question? Yeah. So instead of incentivizing, what if you penalize people for not being part of? Sorry, what do you think that would actually help?
Yeah, I mean, so this is kind of the stick versus carrot debate. I mean, it's difficult to use a stick at present because of.
But if a utility decided.
I can't, right? I can't just say I'm going to force you to participate in this experimental program. So it has to be optional where they're paid for providing something to the system as opposed to being penalized for not providing something. But in the future, we will, I think, converge on mechanisms of that type because there's no need to measure baselines, right? You just increase price when, for the customer when the wholesale price is high, and they'll reduce their demand. That's it. So,
the airline companies do this.
Yeah, but it's difficult to do at present. But that's.
You can give them upfront some amount, and then if they don't participate, take it back. So they should.
Yeah, no, that's
the feeling that they lose something.
That's right. That's actually related to another incentive design that a utility in Singapore used. Was they required customers to pay for their electricity at the beginning of the month. Okay, and so they'd have these credits, and they could see how the credits were being depleted over the month, and so they found that they were actually able to reduce demand. by just having customers pay closer attention to losing money, right? So. Yes.
So I think in that transportation setting that you mentioned, just kind of inspiring this, there's something about the salience of, or sort of like the visibility of the people who win big, making a big impact on participation. I wonder if you thought about like what that would look like at some larger scale as well.
Yeah. So if I think, if I see my buddy or my neighbor won a reward, right? It's like, well, actually, there's a chance of winning, perhaps, right? It might amplify my.
Like if someone on your block won a reward,
Yeah.
this might.
So we haven't studied that explicitly, but the mechanism we're running now is we're designing that we will implement is a procurement point mechanism where buildings have to collaborate, so they only receive a payment if they meet some threshold in demand reduction. And so, so these ideas of leveraging on social interactions and group action, I think, is interesting. But it's different. It's slightly different than what you mentioned.
Maybe we should take the questions offline in the interest of time. Thanks, Eilyan, again. Start again at 1:30 for the last talks.